In a dryer circuit, the neutral conductor is indeed counted as a current carrying conductor, or CCC, for derating purposes. This is because the neutral carries the imbalance current between the two hot legs in a split-phase system like those commonly used for dryers. When conductors are bundled together, the heat generated by the current flow can cause the insulation to break down more quickly. To compensate for this, the ampacity of the conductors must be derated. The National Electrical Code, or NEC, provides tables and guidelines for derating conductors based on the number of current-carrying conductors in a raceway or cable. If, after derating, the ampacity of the conductor is determined to be 28 amps, the wire would need to be upsized to number 8 American wire gauge, or AUG. A 30 amp breaker would not qualify as the next size up in this scenario. The reason is that the overcurrent protection device, such as a circuit breaker, is designed to protect the conductor from overloads and short circuits. The breaker must be sized to protect the conductor's ampacity. In this case, using a 30 amp breaker on a conductor with a derated ampacity of 28 amps would not provide adequate overload protection. The NEC generally allows for the next standard overcurrent device rating to be used if the conductor ampacity does not correspond to a standard breaker size, but there are specific rules that must be followed. This allowance is typically found in NEC section 240.4b. However, this exception is not applicable when the calculated ampacity is 28 amps and a 30 amp breaker is selected. It is critical to remember that overcurrent protection is designed to protect the conductors from thermal damage, not necessarily the load itself. The size of the conductor is determined by the calculated load, derating factors, and the allowable ampacity of the conductor insulation type. The overcurrent protection device protects the conductor from excessive current that could cause overheating and potentially a fire. For a dedicated load, the actual load cannot be used for wire size calculation. The wire size must be calculated based on NEC Table 310.16 or other applicable tables and sections in the code. NEC Table 310.16 provides the allowable ampacities of insulated conductors rated up to and including 2000 volts, 60 degrees Celsius through 90 degrees Celsius in free air based on an ambient air temperature of 30 degrees Celsius. This table is a fundamental reference for determining the correct wire size for a given application. For a 30 amp circuit, NEC Table 310.16 requires the use of number 10 AWG wire for copper conductors with 60 degrees Celsius insulation, or number 12 AWG wire for aluminum conductors with 60 degrees Celsius insulation. The table also provides ampacities for conductors with high temperature ratings, such as 75 degrees Celsius and 90 degrees Celsius. It is important to select the correct conductor insulation type based on the temperature ratings of the terminations and equipment being used. Additionally, any applicable correction factors for ambient temperature and adjustment factors for the number of current carrying conductors must be applied to the allowable ampacities in Table 310.16. In a commercial application, it is essential to adhere strictly to the NEC guidelines to ensure electrical safety and compliance. The NEC provides a comprehensive set of rules and regulations for electrical installations, and it is the responsibility of the electrical contractor or installer to be familiar with and follow these rules. The consequences of not following the NEC can be severe, including electrical fires, equipment damage, and even injury or death. When calculating the required wire size for a circuit, it is important to consider all applicable factors, including the load current, voltage drop, ambient temperature, number of current carrying conductors, and the type of conductor insulation. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Ambient temperature is the temperature of the surrounding air. High ambient temperatures can reduce the ampacity of conductors. The NEC provides correction factors for ambient temperatures that are higher than 30 degrees Celsius. The number of current carrying conductors is the number of conductors in a raceway or cable that carry current continuously. When multiple current-carrying conductors are bundled together, the heat generated by the current flow can cause the insulation to break down more quickly. The NEC provides adjustment factors for the number of current-carrying conductors. The type of conductor insulation is another important factor to consider. Different types of insulation have different temperature ratings. It is important to select the correct insulation type based on the temperature ratings of the terminations and equipment being used. In summary, when sizing conductors for a dryer circuit in a commercial application, remember these key points. Firstly, the neutral conductor is counted as a current-carrying conductor for derating purposes. Secondly, after derating, ensure the conductor ampacity is adequate for the load, and a 30 amp breaker might not be suitable if the derated ampacity is 28 amps, requiring upsizing the wire to number 8 AWG. Thirdly, the wire size must be calculated based on NEC table 310.16, and the actual load cannot be used alone for wire sizing. Adhering to these guidelines ensures electrical safety and NEC compliance in your commercial installation. Let's delve deeper into NEC table 310.16 and its application. This table is the cornerstone for determining the allowable ampacities of conductors. It categorizes conductors by their insulation type and temperature rating. Common insulation types include THHN, THWN, and XHHW, each with different temperature ratings, typically 60 degrees Celsius, 75 degrees Celsius, and 90 degrees Celsius. The table provides ampacity values for each insulation type based on the wire gauge. For example, a number 12 AWG copper conductor with THHN insulation, which has a 90 degrees Celsius rating, has a higher ampacity than a number 12 AWG copper conductor with TW insulation, which has a 60 degrees Celsius rating. When using table 310.16, it's crucial to select the appropriate column based on the termination temperature rating of the equipment. The NEC typically requires that conductors to be terminated at equipment rated for 75 degrees Celsius or higher. However, in some cases, equipment may be rated for only 60 degrees Celsius. In such cases, the ampacity of the conductor must be based on the 60 degrees Celsius column in table 310.16, even if the conductor insulation is rated for a higher temperature. This is because the termination is the weakest link in the circuit, and the conductor ampacity must be limited to the temperature rating of the termination. In addition to table 310.16, the NEC provides other tables and sections that may be relevant to wire sizing. For example, table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. This table reduces the allowable ampacity of conductors when multiple conductors are bundled together. The amount of derating depends on the number of current-carrying conductors and the insulation type. For example, if there are 4 to 6 current-carrying conductors in a raceway, the allowable ampacity of each conductor must be reduced to 80% of its value in table 310.16. This derating is necessary to prevent overheating of the conductors due to the cumulative heat generated by the current flow. Another important factor to consider when sizing conductors is voltage drop. Voltage drop is the reduction in voltage that occurs along the length of a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To calculate voltage drop, you can use the following formula: voltage drop equals 2 times K times I times D divided by Cm, where K is the direct current resistance factor, typically 12.9 ohms for copper and 21.2 ohms for aluminum. I is the current in amps, D is the one-way distance in feet, and Cm is the circular mils of the conductor. The circular mils of a conductor can be found in NEC Chapter 9, Table 8. If the calculated voltage drop exceeds the recommended limits, you will need to increase the size of the conductor to reduce the resistance and lower the voltage drop. In addition to the NEC requirements, there may be local codes or regulations that apply to electrical installations. It is important to check with the local authorities to ensure that your installation complies with all applicable codes and regulations. Proper wire sizing is critical for electrical safety and performance. By following the NEC guidelines and considering all applicable factors, you can ensure that your electrical installations are safe, reliable, and code compliant. Remember to consult with a qualified electrical professional if you have any questions or concerns about wire sizing or any other aspect of electrical work. Furthermore, let's consider the implications of using the next size up rule for overcurrent protection. NEC Section 240.4b allows for the use of the next highest standard overcurrent device rating, provided certain conditions are met. This provision is intended to address situations where the calculated conductor ampacity does not exactly match a standard breaker size. However, it is crucial to understand the limitations of this rule and apply it correctly. The next size up rule is not a blanket authorization to use any breaker size that is larger than the conductor ampacity. It is subject to specific limitations and conditions outlined in the NEC. One key limitation is that the next size up rule only applies if the calculated conductor ampacity does not correspond to a standard overcurrent device rating. For example, if the calculated ampacity is 22 amps, and the standard breaker sizes are 15 amps, 20 amps, and 25 amps, the next size up rule would allow you to use a 25 amp breaker, provided the other conditions of the rule are met. However, if the calculated ampacity is 28 amps, as in the scenario described, the next size up rule does not apply because there is a standard breaker size, 30 amps, that is close to the calculated ampacity. In this case, using a 30 amp breaker would not be permitted because it would not provide adequate overload protection for the conductor. Another important condition of the next size up rule is that the overcurrent device must not exceed the ampacity of the conductor being protected. This means that even if the calculated ampacity does not correspond to a standard breaker size, you cannot use a breaker that is larger than the conductor's ampacity. For example, if the calculated ampacity is 18 amps, and the standard breaker sizes are 15 amps and 20 amps, you cannot use a 20 amp breaker because it is larger than the conductor's ampacity. In this case, you would need to use a 15 amp breaker or increase the size of the conductor to allow for a larger breaker. The next size up rule is also subject to specific requirements for certain types of circuits and equipment. For example, the NEC contains specific rules for overcurrent protection of motor circuits, which may limit the applicability of the next size up rule. It is important to consult the applicable NEC sections to determine whether the next size up rule is permitted in your specific situation. In addition to the NEC requirements, manufacturers' instructions may also provide guidance on overcurrent protection. Some equipment manufacturers may specify the maximum overcurrent device rating that can be used with their equipment. It is important to follow the manufacturer's instructions to ensure that the equipment is properly protected. Using the correct size overcurrent device is essential for electrical safety and equipment protection. An undersized breaker may trip unnecessarily, causing nuisance outages. An oversized breaker may not trip quickly enough to protect the conductor or equipment from damage. By following the NEC guidelines and considering all applicable factors, you can ensure that your overcurrent protection is properly sized and provides adequate protection for your electrical system. Understanding the intricacies of conductor ampacity, derating factors, and overcurrent protection is paramount for any electrical professional. The NEC serves as the ultimate guide in ensuring safety and compliance in electrical installations. Ignoring its provisions can lead to hazardous situations and costly consequences. Remember to always consult the latest edition of the NEC and seek guidance from qualified electrical professionals when in doubt. By staying informed and adhering to best practices, we can collectively contribute to a safer and more reliable electrical environment. Consider a scenario where a dryer circuit is installed in a commercial laundry facility. The dryer is rated for 5,000 watts at 240 volts. The circuit is wired with number 10 AWG copper conductors with THHN insulation, which has an ampacity of 30 amps according to NEC Table 310.16. The circuit is protected by a 30 amp circuit breaker. However, the conductors are installed in a raceway with 6 other current-carrying conductors. According to NEC Table 310.15b3a, the allowable ampacity of the conductors must be reduced to 80% of their value in Table 310.16. This means that the derated ampacity of the number 10 AWG conductors is 30 amps times 0.80, which equals 24 amps. Since the derated ampacity of the conductors is only 24 amps, the 30 amp circuit breaker is too large and does not provide adequate overload protection. In this case, the conductors would need to be upsized to number 8 AWG copper conductors with THHN insulation, which have an ampacity of 40 amps according to NEC Table 310.16. The derated ampacity of the number 8 AWG conductors would be 40 amps times 0.80, which equals 32 amps. This is sufficient to carry the load current of the dryer, which is 5000 watts divided by 240 volts, which equals 20.8 amps. The circuit could then be protected by a 30 amp circuit breaker. This example illustrates the importance of considering all applicable derating factors when sizing conductors. Failure to do so can result in undersized conductors that are not adequately protected by the overcurrent device. In addition to derating for the number of current-carrying conductors, other derating factors may also apply. For example, conductors installed in high ambient temperatures must be derated to account for the increased heat. The NEC provides correction factors for ambient temperatures that are higher than 30 degrees Celsius. Conductors installed in underground ducts or conduits may also need to be derated due to the limited heat dissipation. The NEC provides specific rules for derating conductors in these situations. It is important to carefully review the NEC requirements and consider all applicable derating factors to ensure that your conductors are properly sized and protected. Remember, electrical safety is paramount, and proper wire sizing is a critical component of a safe and reliable electrical system. By following the NEC guidelines and consulting with qualified electrical professionals, you can ensure that your electrical installations are safe, code compliant, and perform as intended. Voltage drop calculations are vital to ensure efficient and reliable operation of electrical equipment. Excessive voltage drop can lead to reduced performance, overheating, and even equipment failure. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, it is essential to select conductors with adequate size and minimize the length of the circuit. Consider the scenario of a commercial kitchen where a 20 amp, 120 volt circuit is run to supply a food processor. The circuit is wired with number 12 AWG copper conductors, and the distance from the panel board to the food processor is 100 feet. Using the voltage drop formula mentioned earlier, we can calculate the voltage drop for this circuit. Voltage drop equals 2 times K times I times D divided by Cm, where K is 12.9 ohms for copper, I is 20 amps, D is 100 feet, and Cm is 6,530 circular mils for number 12 AWG copper conductors. Plugging these values into the formula, we get voltage drop equals 2 times 12.9 times 20 times 100 divided by 6,530, which equals 7.9 volts. The percentage voltage drop is voltage drop divided by source voltage times 100, which equals 7.9 volts divided by 120 volts times 100, which equals 6.6%. Since the voltage drop of 6.6% exceeds the recommended limit of 3% for branch circuits, the number 12 AWG conductors are too small for this application. To reduce the voltage drop, the conductors would need to be upsized to number 10 AWG copper conductors. The circular mils of number 10 AWG copper conductors is 10,380. Using the same formula, we can calculate the voltage drop for the circuit with number 10 AWG conductors. Voltage drop equals 2 times 12.9 times 20 times 100 divided by 10,380, which equals 5.0 volts. The percentage voltage drop is voltage drop divided by source voltage times 100, which equals 5.0 volts divided by 120 volts times 100, which equals 4.2%. While the voltage drop is still above the NEC recommendation of 3%, it is at least within the allowance for feeders, and much closer than the previous scenario. In addition to upsizing the conductors, other methods can be used to reduce voltage drop. One method is to reduce the length of the circuit. The shorter the circuit, the lower the voltage drop. Another method is to increase the voltage of the circuit. The higher the voltage, the lower the current and the lower the voltage drop. However, increasing the voltage may not be feasible in all situations. It is important to consider all applicable factors when designing an electrical circuit to minimize voltage drop and ensure efficient and reliable operation of electrical equipment. Voltage drop calculations should be performed for all circuits, especially those that are long or carry heavy loads. By carefully considering the factors that affect voltage drop and taking appropriate measures to minimize it, you can ensure that your electrical system performs optimally and provides reliable power to your equipment. In conclusion, properly sizing conductors and minimizing voltage drop are essential for electrical safety, equipment protection, and efficient operation of electrical systems. By following the NEC guidelines, considering all applicable factors, and consulting with qualified electrical professionals, you can ensure that your electrical installations are safe, code compliant, and perform as intended.